Welcome back to the exam walkthrough. We're going to be going through 2023 October, question number 15 and question number 20. Pause the video, do the questions yourself, and then watch me explain and solve the question. So question number 15 says the nuclear model of atom was developed after a series of experiments in which alpha particles were directed at thin gold foil. An alpha particle with kinetic energy of 5.52 mega electron volts approaches a gold nucleus head-on, as shown. The alpha particle is brought to rest and then returns along its original path. Calculate the minimum distance between the alpha particle and the gold nucleus. So the alpha particle is going to have the maximum kinetic energy and its electric potential energy is going to be 0. Then as it comes closer to the gold nucleus, because they both are positive, so alpha particle has protons and the gold nucleus also has protons, so both of them have protons, there's going to be repulsion. Because of that, the kinetic energy will start to decrease and the electric potential energy will start to increase. And then at this point, the kinetic energy will be 0 and the electric potential energy will be maximum. And this is called the point of minimum distance. So this is when the distance is going to be the smallest it can be. Beyond this, the alpha particle cannot get any closer, and so it will just return to its original path then. That's what this point means. The alpha particle is brought to rest and then it returns to its original path. So when Ke is 0, Ep is max, alpha particle stops here, distance becomes minimum, and it goes back. So I hope that's clear. Which means what we can say here, essentially, is that all of your kinetic energy changes into electric potential energy. Again, all of your kinetic energy changes into electric potential energy. So I can say that the loss in Ke is equal to the gain in the electric potential energy. And then what I can say next is that we know the kinetic energy that's given to us up there. It is in mega electron volts, but we can change it. So what we can say here then is that the EPE is equals to Q times V, which is the electric potential. And then we can expand the formula and we can write, we know the electric potential is equals to KQ over R. So we can hence get the formula K capital Q small q over R. This is the capital Q and this is the small q. Okay, the small q is a charge whose electric potential energy and kinetic energy are changing. So now what we can do here is we know that the electric potential energy at the minimum distance is going to be equal to the kinetic energy that was there initially. Now first things first, let's change that 5.52 mega electron volts into joules. So we know 1 EV is equals to 1.6 times 10 to the power of minus 19 joules. And 1 mega EV is going to be equaling to 1.6 times 10 to the power of minus 13. We're just taking both sides and multiplying both sides by times 10 to the power of 6. And this side also by 10 times 10 to the power of 6. Both sides multiplied by that gives us this. And now we can solve this equation for finding how much energy is in joules for 5.52 mega EV. We just cross multiply. Now that we cross multiply and solve, we should get the energy as 8.832 times 10 to the power of minus 13 joules. So now we know the value of the electric potential energy. All we have to do now is find the charges. So here, this number below, it's called the proton number. It shows us the number of protons present. The number up here is going to be the number of protons plus the number of neutrons. We care more about this smaller number. Basically this 2 here means there are 2 protons here. And the 79 means that there are 79 protons here. And we know the charge on 1 proton is going to be 1.6 times 10 to the power of minus 19 coulomb. Okay, that's right. Now all we have to do is we just have to multiply this number with 79 and with 2 respectively for both of them. And we can get the charge for both of them and then multiply the charges. Now here what I've done, I've plugged in the value of my electric potential energy at the minimum distance, value of K, 2 times the charge on a proton. This is going to be the charge on the alpha particle, and this is going to be the charge on the gold nucleus, right? Yeah, gold nucleus. So 79 times the charge on a proton. And then now we can solve for our minimum, which is going to get us, and that's going to get us 4.12 times 10 to the raised power of minus 17 meters. So that's the minimum distance. And then it says an alpha particle with a different energy approaches the gold nucleus, and the minimum distance between this alpha particle and the gold nucleus is 5.68 times 10 to the raised power of minus 14 meters. Calculate the maximum electrostatic force that acts between this alpha particle and the gold nucleus. Remember that at the minimum distance, the electrostatic force of repulsion will be maximum, and the acceleration also will be maximum, and the alpha particle will be repelled away and move with the maximum acceleration and also maximum electrostatic force of repulsion when it reaches its minimum distance with the gold nucleus. Okay, this is important because in another past paper what they did was they wanted you to find the acceleration at the minimum distance. So you have to take this distance and put it in the equation F is equals to ma, where this F was kqq over r square is equals to ma. So that type of question can also be asked. Okay, but this is just an important point to highlight here. Okay, this question is pretty simple. You just have to use kqq over, or kq1 q2 over r square, and you're just going to plug in the values. So I've plugged in all the values. You already know all of these values from the previous part. Just plugged in the minimum distance square. Now I'm going to get the force. So you're going to get the answer as 11.3 newtons. And that's all for this question. Okay, I hope that was clear. Now we're going to be moving on to question number 20. Now it's a lot of things to read, so I want you to pause and read the question very carefully. If I read it, it's just going to waste a lot of time. So read it and I'm going to answer the question. Now it says in the question, after the sphere has been charged, the sphere starts to oscillate between the plates and the sphere touches each plate alternately. Explain why the conducting sphere oscillates between the two plates. So let's say the sphere is negatively charged. This plate is going to be positively charged. This is going to be negative because this side is connected to this plate is connected to the positive side of the battery, and this plate is connected to the negative side of the battery. So the sphere will attract towards the positive plate because the plate and the charge on the sphere, they're both of opposite polarity. And then once the sphere comes into contact with the positive plate, the sphere becomes positively charged. And now they have the same polarity, so the positive is gonna repel each other, the positive sphere and the plate, and then the sphere will be attracted towards the negative plate now. And once it's attracted to the negative plate, it touches the negative plate, it's going to become negatively charged. Again, they repel because same polarity, and it's going to be attracted towards the opposite polarity, which is positive, and then it's just going to move around like that. So I hope that was clear. I tried to kind of give you an overall picture. Basically, that's what you have to write here. So the answer to this question will be the charged sphere will be attracted towards the plate with the opposite polarity. Once the sphere touches the plate, the sphere's polarity changes to the polarity of the plate. Same sign, so they're going to have the same sign. So the sphere repels due to the electric force exerted on the sphere, and it is attracted to the other plate with the opposite polarity. And so it just moves alternately between the plates. So that's going to be your 3-mark answer. There are other ways you can write this as well. You can check the mark scheme for that, which is going to be at the end of the video. Next question, it says, a few years later, another scientist called Franklin adapted Gordon's device. Franklin suspended a conducting sphere between two metal bells. One metal bell was connected to Earth, and the other metal bell was connected to a lightning conductor, as shown. During an electrical storm, the sphere oscillates between the bells and the bells ring. The lightning conductor is a long wire attached to the top of a building. The lightning conductor becomes positively charged when in an electric field. The conducting sphere is initially uncharged. Explain why the conducting sphere starts to move between the bells during an electrical storm. Now, during an electrical storm, what's going to happen is that there will be an electric field around the lightning conductor. And we know from the information in the question that the lightning conductor will become positively charged when in an electric field. Remember, during an electrical storm, there is an electric field. So hence, the lightning conductor will become positively charged. And what's going to happen to the conducting sphere because of that is it is going to be attracted to the bell that is connected to the lightning conductor. So the electrons inside of this conducting sphere will move to the right side because they're attracted to the positive charge, and because of that the electrons will move to the right hand side. And due to this, the conducting sphere will be attracted to the bell on the right hand side. That's basically why the conducting sphere will start to move between the bells. So you're going to write that the bell connected to the lightning conductor also becomes positively charged. So the bell here is also positively charged because the lightning conductor becomes positively charged. And because of that, the electrons in the conducting sphere move towards the bell on the right side, and the sphere is attracted to the bell on the right hand side. That's basically going to be your 2-mark answer. Of course, I've given you a lot of space, but the answer is quite concise and short. Okay, so I hope that was clear. And that's all for this video. Now I'm going to show you the mark scheme and the examiner report.